there's one more ingredient that we need before we can start doing calculations for thermodynamic cycles with phase transitions. That is a quantity called enthalpy. Enthalpy hasn't been too different from what we've discussed already, but it just hasn't been a real necessity. So let's go through the basics and definitions of enthalpy right now. For a single component system, enthalpy is a quantity which behaves or has a similar idea behind it to internal energy. However, it's different by an additional term. The enthalpy is H, and it's defined as the internal energy plus the product of the pressure and the volume. So it's a type of energy. In fact, internal energy and enthalpy are both quantities which we will later group into a class called thermodynamic potentials. Now, what's the benefit of defining a quantity that's equal to U plus PV? We can find out by taking the differential of H. For now, we'll just write the differential of U as du. For the differential of product of pressure and volume, we must use the product rule. Pressure times a small change in volume plus volume times a small change in pressure. Now we'll focus on the du, and to substitute the fundamental thermodynamic identity. Du is equal to T times a small change in entropy minus the pressure times a small change in volume plus the chemical potential times a small change in the number of molecules. The other two terms are still here. But we've achieved some cancellation now. The minus PdV term from the fundamental thermodynamic identity and the plus PdV term that came from adding PV up here cancel each other out. So the differential of the enthalpy is temperature times a small change in entropy, which we can still associate to heat. The next term is the volume times a small change in pressure. This doesn't really have an interpretation as a work, but it is a form of an energy change. And lastly, we have the chemical energy term, which usually doesn't change in thermodynamic cycles, heat engines, and refrigerators. The important thing to notice about the enthalpy is that now we've expressed it in terms of changes in entropy, or heat, changes in pressure, and changes in number of particle. So the enthalpy has a special relation to situations where the pressure is held constant, that the internal energy doesn't share. When the pressure and the number of molecules are constant, changes in the enthalpy are exactly equal to the heat absorbed by the system. This is why we use the symbol H for enthalpy. In older materials, the enthalpy was thought to represent the accumulated heat inside the substance. If you do all of your experiments at constant pressure, then delta H and Q are the same thing. The reason that this helps us for analyzing thermodynamic cycles is we're often interested in the amount of heat absorbed or heat ejected by a substance. To look at a PV diagram and immediately extract the heat value is very difficult. But if we know the enthalpy values in a table for all sorts of different places on the PV diagram, and we want to know the heat absorbed or ejected between two locations, we only need to look up the enthalpy value at the start and the end of that process. And that difference will then tell us the amount of heat absorbed.